Hello everyone and welcome to Seminar 3 of the CHE 446 course. This seminar serves as a demonstration for simulating ordinary differential equations in MATLAB, which makes up question 4 of Lab 2. The topics covered by the problems in this seminar are broadly classified as follows. We start with an introduction to the tasks in Lab 2. The step-by-step procedure and background theory for each task is detailed in the manual, but I will present a broad overview in this video. The main objective of this video is to demonstrate how to solve ODEs or ordinary differential equations in MATLAB using the inbuilt solver called ODE 45. For this demonstration, we will go through the simulation of a simple chemical reactor process. If you are unfamiliar with the MATLAB environment or basic commands, you can refer to a separate primer uploaded on eClass. Let us start with an overview of the tasks in Lab 2. For the single heated tank system, you are asked to conduct mass and energy balances for the tank. You are then asked to obtain a mathematical description of the tank system in the form of a system of differential equations. Then, you are asked to linearize the system around given steady-state conditions. You are asked to convert the resulting multi-input, multi-output or MIMO system into a single input, single output or SISO system. For the simpler system, you are asked to formulate it as a transfer function between temperature of tank liquid and steam flow. Finally, you are asked to simulate the system described by the ODEs in MATLAB. This is the main objective of this seminar. Questions 1 and 2 of Lab 2 relate to conducting mass and energy balances on the tank. This is done using the laws of conservation of mass and energy as follows. When you model any system, make sure to always state all the assumptions made very clearly and to always report all numerical values with their units. For question 3, use the equations developed in questions 1 and 2 to obtain the system of ODEs that describes the tank system. Then, obtain the linearized version of the ODEs around nominal conditions. Convert the system, which is currently a multi-input, multi-output system, into a single input, single output system. You can figure out which input and output variables to consider unchanging by referring to your problem statement. Then, obtain the transfer function of the simplified SISO system by taking the Laplace transform of the equation. Make sure that when you report the final transfer function model and identify the coefficients in the model to include their units as well. In question 4, you are asked to perform two simulations. One using the original MIMO system resulting from the mass and energy balances in questions 1 and 2, and the other using the linearized MIMO system from question 3. For both simulations, you are asked to plot the response of the system when there is a step change of 0.5 kg per minute in the cold water inflow to the tank from its steady state value. Finally, you are asked to compare and analyze the responses resulting from both simulations. In order to solve question 4, of course, the main thing you need to know is how to simulate a system of ODEs in MATLAB. Let us consider a simple example of a process occurring within a chemical reactor. Two compounds A and B react to form compound C through the reaction given as follows. Compound C further breaks down into a less favorable compound D through the reaction given here. We are told that the volume of the reactor is 10 meter cube. For industrial manufacturing purposes, we need to know how long it takes for steady-state production of C when the reactor starts from initial conditions, and what is the response of the system in terms of concentration of compound C when flows of compound A and B into the reactor are changed. In order to simulate this reactor system, we must first find the system of ODEs that describe it. The reactor process can be described through the following component balance equations given as follows. With these equations in hand, we now proceed to the MATLAB environment. Let us now start coding in MATLAB. We start by creating a new script file and saving it in its separate folder on the desktop. So first, I go to the desktop, create a separate folder called seminar_3, into which I am going to save this new script file with the name new_process. So once I hit save, I go to this script file and start putting in the parameter information for this system. Now the parameter information can be found in the problem statement. One suggestion is that you use a naming convention that makes as much sense as possible. So for example, the volume of the reactor is represented by V, the rate constants by K1 and K2. VA in represents the volumetric flow rate of compound A into the reactor, and similarly for VB in. CA in equals 1 and CB in equals 1. These are the inlet concentrations of compounds A and B. We give the parameter volumetric flow rate out of the reactor equals the sum of the volumetric flow rates into the reactor, which means it's a constant volume reactor. And finally, we put in some comments related to each parameter, which describe what the value actually is. Because when you come back to this code after a long time, you may not actually remember what V, K1, K2, etc. actually stand for. So it is always important to put in some comments in your code so that it is easy for you to refer back to it when you come back after a long time. Or if you have to pass this code on to somebody else who has perhaps used different naming conventions. So that is always a good practice to keep it consistent between your own codes and between transferring to other people. So we put in a couple of comments for the concentration compounds here and for CB in as well. And another good thing about putting in these comments is including the units for each of these parameters within the comments so that you can inherently perform a unit or dimensionality analysis check to see that you are actually using the right units in case you have to perform any calculations in this function file using these parameters, which we will have to do, as you can see. Now it comes to associating the outputs of the system and the internal input argument y. I will explain this in a moment. This script file is defined in the form of a function file that can be called by other script files to perform specific computations which are coded within this file. So the input arguments to this function file are first a dummy time vector t and secondly the vector y. As we have defined further on in the function file, y contains values corresponding to each of CA, CB, CC, and CD. And this is the main outlook of how a function file actually looks in every case. So once the association has been made, we define the 4 ODEs that describe the reactor process as follows. The LHS indicates that the ODEs are stored in a column array format, just like you would organize when you assemble the system of ODEs by hand. So we put in the ODEs related to component balance of compound A. Similarly for compound B, which is the second element in that column array. And it's a little bit slow typing these out. I apologize for the delay. But once we've got all of the ODEs coded in, we can proceed with solving those ODEs using MATLAB. So we just have to enter in the component balance equation for compound C. And similarly, we have the component balance for compound D, and that is the final element of that column array. And once we have that coded, it is important to note that you cannot run a function file on its own. Let us try to run this function file anyway and see what happens. First, you may have to change the folder, of course, and then you get an error which says not enough input arguments. So this is always going to happen if you try to run a function file. So now let us create another script file called main_file and save it in the same location as the function file. This is very important. The location has to be the same. Usually, if a script file is not a function file, it is good practice to clear all the variables in the workspace, close any open figures, and to clear the command window screen. So now let us call the ODE45 solver to compute the concentration profiles of the compounds in the reactor process. On the LHS, the first argument, Tout, represents a set of points in time for which the concentrations of compounds A, B, C, and D are computed and stored in the matrix Yout. ODE45 takes in the following input arguments. It takes in, firstly, the function file that contains the system ODEs. Next, it takes in the time span across which it must simulate the ODEs. In this case, from 0 seconds to 7,200 seconds. And finally, it takes in the initial values of output variables in the form of an array. In this case, they contain the concentrations of A, B, C, and D at the start of simulation time, that is at t equals 0. And this is pretty much all you need to run ODE45. These three input arguments. However, you can also add a couple of options to the solver. For example, here I can check that the relative tolerance should be a certain value. And I can also set a different value for the absolute tolerance. And if you don't want to toggle with these tolerances, if it's not necessary, you can just ignore this entire line of options equals ODE set. ODE45 will just run without any specific settings. So if you run this function, if you run this main file, not the function file, you can see in the workspace that we have Tout and Yout. And you can see that they are just some arrays which don't really make sense when you look at it that way. So that is why we are going to plot the profiles of the concentrations of compounds A, B, C, D in the same figure so that we can see how each compound concentration varies across the time span we have decided, from 0 seconds to 7,200 seconds. So you can use the plot command uh, where Tout is going to be your x-axis values and Yout. The first column contains the concentrations of compound A, the second contains concentrations of compound B, third related to compound C, fourth related to compound D. And we can add in the X label and Y label for the axes on the figure. Over here, I have to actually switch it over because the Y-axis relates to concentration and the X-axis relates to time. And adding in some legends is always pretty necessary for plots which contain multiple profiles within the same figure, because otherwise you're just going to get a bunch of lines and you don't know which curve corresponds to which concentration. So we put in the legends, save the file, and now we can run it to actually see in a graphical representation how the compound concentration profiles vary. Um, Here you go. This is the figure that we end up with. And as you can see, the y-axis actually has a bit of a few more values than the time span. And that's why it looks a little bit untidy, just having this white space over here. So we can actually choose what the x-axis should terminate at what value it should terminate using the x limit. So let's set that as the same as the time span and see how the plot looks. It looks much cleaner now. You can just move the legends such that it's not obscuring any profile. And it's a pretty clear plot that depicts how your reactor process works. And you can also save the figure, or you can just go back to your main file and run it for different initial conditions as and how when you require it. So there you have it. That is all for seminar 3. I hope this helps you in finishing up your questions for Lab 2. As I mentioned previously, the MATLAB primer uploaded on eClass has enough information to bridge any gaps in your knowledge for this seminar and lab. However, you are still free to ask me more questions in the upcoming Q&A sessions or through email. Thank you and see you in the next video.